Okay, so we are then continuing with the second part of the chapter on matching. So far we looked into cross-correlation as one technique for matching two images or for matching a small image region with a larger image and trying to find where the image region as an input, the query, to which area in the larger image it fits to, so that we can actually localize a certain sub-image or small area within a larger image. And we present a technique for that, which is called cross-correlation, which is basically an exhaustive search through the image using the template, trying to maximize a certain function, trying kind of at every position, if we get a good match between our template and our image, thereby being invariant under changes in brightness and changes in contrast. So we could actually find the small location of the template in terms of a translation in x and y direction, so it's kind of the offset, under the assumption that the template and the original image only differ in terms of contrast or brightness, or are of course the same. And we found presented a technique which was able to do that. And this is important for a large number of different tasks. Often I need to make correspondences between images, and one of the most prominent tasks was 3D reconstruction. So if I know from which location those two images have been taken, and I know which points in image number 1 correspond to the same object, and I know where they are in the image number 2, so I know, for example, that this point corresponds to this point, so this is the correspondence here, or these two are corresponding points in two images. If I have that information, I can actually estimate the 3D location of those points in the scene. And estimating the 3D location from images is a very relevant task in photogrammetry, because we are typically interested in estimating a 3D model from a sequence or a couple of images. So we have multiple images which are projections from the 3D world onto the 2D image plane, and we have them taken from different positions, and if we know those corresponding points, so which pixel in image number 1 comes from an object and where this same point can be found in the second image, so they have the correspondence in whatever pixel 1010 in image number 1 corresponds to pixel 1020 in image number 2. If I have this information, this correspondence information, I can then estimate the 3D location of the point in the scene. And this is relevant for a large number of different tasks. This was an example of two aerial images where some special points, we will come to those points during the course here, are highlighted, and what we want to have are corresponding points. So if we know that this pixel over here corresponds exactly to this pixel over here, and I have some information of where those images have been taken, I can actually estimate the 3D location of the object in the scene. And in order to realize or establish such correspondences, I can simply cut out a small area in one image and see where I find this small area in the other image. So I could, for example, cut out the fountain here and then search through the whole image until I find it here. And if I find it here, I know that I have a correspondence between those 2 points. And for this, the cross-correlation can be used. What the cross-correlation did, it tried to maximize a certain function, which takes into account basically how the gradients look like so the standard deviations of the intensity values in our images. And we're trying to find the best translation. So this was a translation in x and y, so that this function is maximized, and this corresponds to a match of the template and the original image. And the cross-correlation technique simply does this by search, in the trivial case, exhaustive search. Simply try all combinations of shifts and select the best one, or I can start with a hierarchical search, that I start on a kind of image of reduced size, try to find a match, and then refine that. However we do that, the one technique is typically faster, but we can also do an exhaustive search. And in this way, simply try all possible shifts, and then select the shift where we actually get the best match. This works very well as long as the search space is low dimensional. In our case, we have a two-dimensional search space, so only a shift in x and y. That's fine, we can do that. But if we have a larger number of parameters, like 5, 6, 7, 8, or even more, then this exhaustive search gets extremely slow because I need to try all combinations. So this is only applicable in practice in a low-dimensional space like an XY shift. And this is one of the reasons why the cross-correlation technique, at least as I presented it here, is only suitable to handle translations. And in the way we used our objective function, this objective function was invariant under changes in brightness and contrast, and therefore we can deal with brightness changes, contrast changes, and translations, but nothing else. So if one of the images is, for example, rotated, let's say by 45 degrees, the cross-correlation method will fail, and it's very unlikely to find a good match. And the second part, or something that we haven't explicitly mentioned last time, but which is the case, that we find this match at a pixel accuracy. So we get a result saying we have an offset, and this offset is an integer value. So let's say we have a shift by 3 pixels. But what we don't have is a shift, for example, by 3.5 pixel, because I compare just pixel to pixel. So the translation estimate comes at the discretization of a pixel. We can't get more accurate than at 1 pixel. We can't get whatever, half a pixel or a third of a pixel in the accuracy, in the matching precision. And the goal what we want to do is we want to extend this method and see how we can actually do the same thing. Well, actually, we start with the output of the standard cross-correlation and try to get more precise, to get a sub-pixel estimate. So that we can say, okay, we don't have a shift by 3 pixel or by 4 pixel, we have a shift by whatever, 3.8 pixel. And this is kind of the key goal. So the result is to get more precise, to kind of, after the cross-correlation has converged and reported its maximum, to kind of refine our solution so that we get a sub-pixel precision. So the first question is, how could that work? So we just have pixels. How can we get a precision which is below 1 pixel? Let's say this is kind of, if you see this 1D or just one dimension illustrated, if these are the different values of my objective function rho, that maximizing the cross-correlation will simply report the highest peak. So we'll say, okay, this is the shift in x and y so that this function is maximized. What we can do now is say, okay, let's take into account the points in the nearby area and simply fit a smooth function through them. For example, like this one. See, the red function now is a smooth function through those black dots over here. And if we look to this function, we can say, okay, here's a value which is slightly larger than the solution that I had. So the goal is today to refine this solution, which is the output of the cross-correlation method, to a new nearby location so that the function value that we have here is higher than the one I had before. Okay? So this is the goal that we have. And how we do this is we take our points, so these black points over here, and simply fit a smooth surface. In this case, it's typically a quadratic function, a quadratic form, so a parabola in 2D or a quadratic form in multiple dimensions. Approximating this function, starting from the best result that we have, and then estimate the maximum of this function. And this typically allows us to refine the estimate, and we can get a better estimate of the translation. So the translation is not an integer value anymore, but a floating point number. And we typically can go down to something like, for example, 1/10 of a pixel. So if we find the alignment, we can actually estimate the translation, for example, with 1/10 of a pixel. So is the objective clear of what we aim at doing now? Yes. Yeah.
When you now put it somewhere in between the pixels, sub-pixels,
yep.
How can you deal with it? Because at the very end you still have an image which is built of pixels and not sub-pixels.
This is true. So if you now consider that, so this typically appears if you have, let's say, a stereo setup, and you want to estimate correspondences in order to estimate the depth information. If I have corresponding points in, let's say I'm working in the beginning just with pixels, I just have a discrete number of depth values which the object can actually be located to. This results from the fact that I have only pixel correspondences. If I now can say, I know that it's not the shift is a multiple of one pixel, I can now say it sits between two pixels. I can actually simply estimate, simply use 3.5 pixel, for example, instead of 3 or 4 pixel, and then do the triangulation.
So you use it only for calculating the distance to the object?
Yeah, so yes, so I typically use this information. I mean, even if I align both images, I could do even an alignment of the image, which is a subpixel alignment, and then I may need to interpolate between those values. But I can use this information that one point in one image corresponds to another point in an image with subpixel accuracy, for example, to do better 3D reconstruction tasks. This is kind of the standard application for that. Further questions on that? Okay. So what we're doing now, we are saying we have a 2D problem because we want to estimate the shift in x and the shift in y. This was been my variables u and v. And what I want to do now, I want to fit the quadratic form near the maximum that I have, or the best maximum estimate of the maximum that I have at pixel accuracy, fit a quadratic form to that, and find the maximum of this quadratic form. Okay, so what we do now is we say, okay, my variable x is a two-dimensional vector with u and v. And x star is my unknown maximum, so this is the quantity that I want to compute. Say, okay, it's a quadratic form, so I have x minus v star here, I have a matrix A plus an offset. What I want to do now is I want to estimate the maximum of this quadratic form. Okay, so in order to estimate the maximum of this quadratic form, in order to find the maximum, we need to compute the first derivative and check at which location the first derivative is 0. Right? Okay, so we take our function, compute the first derivative, and if you have a quadratic form, you should have seen that already in your lectures on least squares estimation from Professor Shu. Then this is the first derivative of our function. And so this value takes the value of 0 if x takes the value of x star, because then this gives 0 and the overall function value takes 0. Okay, so at the maximum, when we know that this is a maximum, at the maximum, our function takes a value of 0. Okay, so we have our first derivative, and then we continue and say, okay, this was our first derivative, so now we can actually compute the Hessian of the function. If we do that, we can actually see that it is simply 2a. So, okay, this is the Hessian evaluated at our at the current best estimate that we have. We can simply take that and plug it into this function over here. So we can rewrite this function as the gradient or first derivative of my function rho is the Hessian of x minus x star. And now I can simply multiply from the left-hand side by the inverse of this function. So the h inverse goes here, it disappears here, and then I can finally transform that by moving this to this side, x star to the other side, and then I have the update rule, x star equals my input value x that I have, the Hessian and the first derivative at that location. And this updates my estimate of the shift in x and y to a subpixel precision, which is the maximum of that function. Okay, now let's have a look how we actually obtain those values for a more concrete example. So we have an image, we have this update rule. Let's see what the individual parameters are. So the x simply consists of my shift in x and my shift in y. So this was just the offset. to the quantities I'm interested in. So this is a 2D variable. Then I have the first derivative, and the first derivative is of the function rho is the first derivative in the I direction, so I corresponds to x. So in the I dimension, I update the shift u, and in the j dimension, I have the update of the shift v. So this is the first derivative in the x dimension and the first derivative in the y dimension, evaluated at the current best estimate that I have at x. And how to compute this is something that we have done actually 2 weeks ago when we looked into local operators. We presented an operator, for example, the Wrobl operator, which allows me to estimate the first derivative of my image function just by a simple convolution. The same holds for, so these elements of the Hessian are the partial derivatives of second order. So these, and we also presented the a filter which I can apply, or a kernel which I can apply by convoluting the kernel and my image function, so that I obtain the derivatives with respect to x, twice y, and x and y. So what I basically do is I obtain those values by applying the Wrobl operator, one in x, one in y dimension, and those 3 different values that I have here by using the operators from the second derivatives. And this was the chapter on local operators and how we are going to do that. So just copied it over, so everything which comes down here is from the chapter of local operators. So I had the Wrobl operator in x direction, so this is x in my image. So you can see here that it takes this value, subtracts this value. This is the smoothing, so this was the center of the kernel. So it was a smoothing in this direction and the derivative in this direction. And I convolve this with my image function, and I do the same for both directions. And the Wrobl operator now provides me exactly those different elements over here. So for every point in my image, I obtain the first derivative. And I can do exactly the same thing with the second derivative. Again, it's a copy-paste from the chapter on local operators. And so I have the derivative with respect twice to u, to uv, and to v, twice to v. And these are the operators that I have. So in order to compute those values, the only thing I need to do, I actually need to use the Wrobl operator in x and y, and I need to use these 3 operators or kernels for my current estimate to estimate what does the gradient look like, what does the Hessian look like, and I have this information, I can directly obtain my subpixel accurate estimate. So what I do in sum, I use the cross-correlation method to find the best match at a pixel accuracy, and then I use this technique. Just everything I need to do is actually written on this slide. So I need to compute those 2 elements by applying these kernels and then execute this rule, and then I end up getting a subpixel accurate estimate of my shift. Of course, this makes the assumption that I have this smooth function, that there is this quadratic form, and that the matching function that I have has this shape. But it's typically a better estimate rather than using a step function for every pixel, which is what I would do if I would simply stop with cross-correlation. So to sum that up, the cross-correlation method provides me the optimal solution if only translations are involved, and if I don't do the subpixel estimate only in discrete steps. If I want to refine that and I assume a quadratic form, so that between the points where I'm sampling for every pixel, I can actually approximate my rho function by a quadratic form. I actually can obtain subpixel estimates, something in the order of 1/10 of a pixel. It's something that I can achieve in practical situations. However, the cross-correlation method has its limitations. Again, if I have rotations or even more complex transformations like affine transformations, I can't apply that because I simply have too many parameters that I would need to search for. The cross-correlation technique can't deal with occlusions, so if those aerial images and I have a bird flying through my image, I have no chance to actually get a good match there if there's a substantial occlusion. And yeah, the cross-correlation also assumes an equal and uncorrelated noise in both images. So that's also one assumption that I do. But if I do a stereo setup with the same camera, for example, this is something which often actually matches. So a few more practical remarks. The cross-correlation also works kind of well if there are kind of moderate violations of those assumptions. So of course, depending on how the template looks like, what the structure of the template is, in most situations, I can even find a good match if I have a rotational offset by something around 20 degrees, or even a little bit less. Let's say if I have 20 or more degrees, it's not, I don't want to say guaranteed because it's not guaranteed at all. It's never guaranteed, but the likelihood of finding the correct match substantially decreases. The same holds if I have a different scale, so if my template is simply scaled up or scaled down. Within a certain range, this can work, but doesn't necessarily has to work. And the key limitation of the cross-correlation technique is the computational time that is needed if I go to higher dimensional spaces. If I, for example, want to take into account rotations, I could simply do an exhaustive search not only in X and Y, but also for every possible rotation of my template. So I can discretize the rotations. Let's say I take 360 different possible rotations and apply the cross-correlation method. I can do that, and in this way also estimate the rotation. The problem is that the complexity grows exponentially with the number of dimensions I need to take into account, because I need to try all different combinations. So even with 3 dimensions, that can get computationally costly, but if I have more complex transformations with something, whatever, 6 or 8 dimensions, this cannot be used or is out of practical use. So the question is now, are there any questions about the cross-correlation method? So it should be clear to you to which problems you can apply the cross-correlation method to, what it can do, what it can't do, so what are the assumptions. If I violate the assumptions, I'm likely to fail and why this is the case. You should have an idea how the approach works, for maximizing a function, and you should have learned today that you can actually get a more accurate correspondences than pixel accuracy. So are there any questions about the cross-correlation method so far? Okay, so if this is not the case, we're going to the next approach, which is called least squares matching, which can be seen as a generalization of the cross-correlation method, in which I want to deal with more complex transformations. So if I have a transformation which is not only a translation, but may involve rotation, scale, shear, or other properties, or different types of radiometric transformations, then I need a more complex technique in order to do that. So we can see that least squares matching is a generalization of the cross-correlation method, supports different types of transformations, but as a disadvantage, as I need that for any nonlinear least squares method, I need an initial guess. And the initial guess matters. So why is this matching a nonlinear problem? Any idea why this is a nonlinear problem? Sorry?
Because you use squares, which is nonlinear.
So no, this is true, but I mean your individual error function or the difference of your model is nonlinear, and this is the problem that we have. So the question is, which of the properties are nonlinear in here? So that I need to iterate as in the standard least square setting. So what I typically have is I have a function, f, which is my image function. And I have an observation of this function, which is, let's say, shifted or transformed in some way. And I have a noise term in there. And the problem is the function that I'm observing is a nonlinear function, because the intensity values in my image are a nonlinear function. I simply take an image, and if I look to the change in intensity value from pixel to pixel, it should be pretty clear that this is a nonlinear function. It's actually a highly nonlinear function in any realistic image that I take. So just look to how do the intensity values change. So I have bright areas, may have steps down to dark areas, increasing values, so I may have temporary linear functions. I again have some noise or some black and white pixels, then I have functions like this. And this is definitely a nonlinear function. So we can do the least squares matching in 1D. And this is something which is often used in signal processing. I say I have one signal over here, and I want to match this with another signal under the assumption that there is a shift in those signals. And in the general case, this shift may even depend on the individual location. So this shift u may be a function. We want to look into even a simpler problem by saying this shift is constant for the whole signal. So just the whole signal is shifted to the left or to the right. I simply have two signals which I want to match. So we say, okay, we just have a shift by a constant u. So this is my constant u. And I have m discrete observations of my signal. So I have a continuous signal. I have some point observations of that signal. And my assumption is that there's a shift between those. So this is my function g, which is my observed signal. So at different locations, xm. So I have m goes from 1 to m, so I have m different observations of the signal. So m sampled points of that signal. Let's say this is a given signal which is shifted. So y is x minus a shift u. So the x changes for every observation, but the u is constant, plus my noise term. Okay, so this should actually be the right slide. The other slide I should have removed. So this leads me to a Gauss-Markov model where this g are my observations plus my noise. So it's depending on how I parameterize this as a noise or an error or residual. It's just a sign can flip, and my function f, which is my nonlinear function. So I have the observations, my function which is shifted, and the noise that I have. So this was the thing in 1D. Now we can do the same thing, and then we can actually solve the Gauss-Markov model, and we actually will do this now in 2D. But we can do this in 1D, and we can do the same thing in 2D because our image is just a 2D signal. So for our image, we do exactly the same thing in 2D. So we have the image, our observation that we have. We have our shifted template. So m is shifted, the x dimension is shifted by u, and the y dimension is shifted by v. It's a constant shift plus our noise term, and we have that for m pixels. What we want to do now is we want to estimate these parameters u and v, so the shift, so that the square of n, the noise, gets minimized. The sum of the squares, sorry. So we want to find the shift, so that's the sum of the squared noise values, so the differences between my observation and my image get minimized. So I want to kind of minimize the mismatch between my observations and my shifted model. I want to find the shift which minimizes that. Okay? So it's kind of the problem that I want to solve clear. So far, I have not done more than cross-correlation. I even have done less than just cross-correlation. I started with the most simple approach in here. So far, I only take into account a shift, but what I don't take into account if I use this formulation is potential changes in contrast and in brightness. So I ignore that for the moment. I'm only looking into a translation. But we can formulate everything here for a translation, and then we simply can add a more complex transformation in there between those images. So my image signal is nonlinear, so f is a nonlinear function. Therefore, we have the need, in order to solve this with our standard approach, that we need to linearize our function f, solve it for the linear approximation of our function, and need to iterate this process. This assumes that f is a continuous function and we can actually compute the first derivative. Otherwise, that would not be possible, of course, but we assume that we can compute the first derivative, and we have seen with those operators that for an image we can actually estimate the first derivative of the image function. Okay, so what we need to do now is we need to linearize our function f. So a potential nonlinear function, or most realistic images are highly nonlinear. So how do we linearize our function? So around an initial guess, we have our function f of x plus some small change in u and y plus some small change in v is our function value at our initial guess, in this case x and y up here. The first derivative with respect to u times the small offset that I have, and the first derivative of this function with respect to y plus the small shift in y. And we can now again rewrite this similar to how we had that before. We simply put that into this equation over here, moved g to the other side. Then we have our function g of m, which is now just a short version of g of xm ym, minus our noise, so our observation minus our noise, is our linearized function. So this is, originally this was just our nonlinear function f, and now it's simply our function evaluated at that position. This is the first derivative with respect to x at location m, and this is the first derivative with respect to y at the pixel location m. So if you kind of, any way I can support you.
I was just wondering, because it's xn and epsilon, isn't it only diagonal?
No, so m is the index for, okay, that's a good point. M is the index for our individual pixels. So I have m pixels. M goes from 1 to m, and these are typically those pixels. So I can just kind of index them as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
I think what you indicate was that normally then, well, we always had then m and n, so we had different indices for both. Now, because they are always the same, it looks like they're going...
Yes, okay, this is true. So this m refers to the pixel, and the pixel are just numbered with a single index. And this x should just indicate the first derivative with respect to x, to which dimension I derive that. I don't think that this notation is absolutely the best notation to use, but this was a notation which was used in the script, and therefore I kind of stick with that is identical to the script. Otherwise, what you could write this is also kind of df with respect derived with dx at the location xm. So kind of df by dx, but then you have this big term which actually sit in here.
Was that it was the index is both times m, and that the so like v, that m is always the same, so it would be always x1, y1, x2, y2, but that's not what you want.
So what I do this, so this is, so m equals 1 refers, in this case, to this pixel over here, which could be x equals 0, y equals 0. M equals 7, for example, would be x equals 1, y equals 2. This is index 0, 1, 2, 3, 0, 1, 2. Okay, so x, yeah. Kind of clear what I meant? Okay. So what I have, if I look to my image, this is again my image with x and y and the changes in u and v. What I then have, so exactly those elements over here, these two guys, is the first derivative of the image function with respect to x and s with respect to y at the location m. So if this is my pixel m, this is my first derivative with respect to y and my first derivative with respect to x. Okay? Okay. again. So this refers to the mth pixel according to this notation over here. Let's just copy paste what we have before. Now we have our linear model, our linear Gauss-Markov model, so we can solve that. You all should know how to solve this. With respect to our two unknowns, which is the shift in x and our shift in y, or a change in shift, so that we can then say update our estimate u is our initial guess plus our delta u, and then I of course iterate this process. Of course I have to iterate it because it's a nonlinear function. So this was so far written for one pixel, but we can also, of course, do this also for all pixels. Then we simply stack them up as G1 to Gm, F1 to Fm. So these are exactly the differences at this location, 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 and so on and so forth. So in this example, I would have 12 elements, G1 to G12 here, for those 12 pixels. Exactly the same what I had before, now just written as the difference between F and G, the noise, and then our Jacobian. So the matrix containing the first derivatives with respect to the individual dimensions. Now once we have that, we can formulate our system of normal equations as being A transposed, the information matrix or inverse of the covariance matrix, which is associated to the uncertainty that I have in my observations, times A, the change in x, and A transposed, the inverse of the covariance matrix, and my delta L. And this directly corresponds to my system of normal equations. So what I typically have now is that the noise that I have in my observations is independent and constant for every individual pixel. If this is the case, the covariance matrix simplifies to an identity matrix times a noise term. So if I say the covariance matrix, simply the variance plus an identity matrix, and this is kind of the noise that I have in the measurements of my intensity values. So I obtain that, for example, if I perform a variance equalization or normalization, what we have done in the lecture on histograms, the fourth lecture, we obtain uniform variance for every individual pixel by this transformation. And once we have that, this simplifies to this form. If this is the case, so these matrix gets replaced by our noise variance times the identity on both sides, so that they can then eliminate it, because this can be moved out, 1 divided by the variance and identity. The inverse of the identity stays the identity, so this simplifies to this expression over here. So if I want to solve that, I could compute the inverse of A transposed A and then obtain my update. Or I use backslash operator in MATLAB, which doesn't explicitly invert that, but for how it's written here, you can actually write this as the inversion. And then I get my update, and I iterate this process because f is a nonlinear function. So I need to relinearize my function and then iterate this process until I converge, and then I have, by adding up the initial guess and all the deltas that I have, I obtain the estimate for the shift in x and in y location. Okay. One thing to note is actually that this shift does not depend on the noise that I have in my image function. So independently of the noise that I have in my intensity values, I obtain the same result for the shift. Of course, depending on how accurate or certain elements of my image are relevant for determining how accurately I can actually estimate this shift. So the image function is not independent of the shift. So the image function matters because there are certain images where I can find an alignment very well, and for others where I can't do that. You may remember the examples that I showed at the end of last lecture for the cross-correlation. So if I have a uniformly colored area and a uniformly colored patch, basically the shift cannot be determined. But if I have a very distinct pattern, I can actually determine that very accurately. And this depends, as we will see in a few minutes, on the gradients of my image function. So the gradients of my image function have a direct relation to how accurately I can actually align my two image patches. But up to the point here, are there any questions about what we have done so far? Yes, please.
Ja, ich habe nochmal zu der Folie mit dem Gauss-Markov-Modell eine Frage. Ja, zu der. G ist ja jetzt das Bild, was wir beobachten, und F ist sozusagen das, was vorher das Template.
So it's yeah, exactly. So the G is our observations, and F is the current model estimate given the current parameters. So it's kind of the mismatch between our observation and our model prediction.
Okay, so we are not looking for a template like in the cross correlation because they have the same size. That's what I was wondering. And for the cross correlation, we had one big picture and we had a small picture which we were looking for.
Okay, so of course, so we can formulate this in exactly the same way as for the. So we could align whole images even if we want to, but it's actually the same within the cross correlation. So this only takes into account the pixels which are involved in the template. So if let's say this is our template, and this is our larger image, for example. I simply look how well does this area fit to the area of my image. I kind of consider only this part because I have only the observations for those pixels here.
And the U and V, where do you find those parameters in this sketch now? So,
so these are.
Die liegen dann trotzdem außerhalb, obwohl man eigentlich nur von beiden Bildern diesen kleinen Ausschnitt bekommt.
So they are implicitly. I think I had that in the beginning. Let's go back. So in my function f, I of course have the shift in there. Because this determines kind of where I start inspecting my f. So the big image would be f in this case. F and have the observations for this area. So these are my 12 observations. Okay, further questions? Okay, the next thing I would like to do is kind of inspect the structure of this matrix, A transpose A, in order to estimate what do we know about how accurately we can actually perform our matching. So A transpose A is the Jacobian transposed multiplied with the Jacobian. So the Jacobian is the matrix consisting of the first derivatives. So this is Jacobian, this is a transposed of the Jacobian, and I multiply them. So I multiply this line with this line, which gives me one element, this line, this line, this line, this line, this line, this line. So I have 4 elements I obtain. And these 4 elements are always sums over m elements. So for example, if I go for the first element, 1, 1, it's this line over here multiplied with this line, the individual elements summed up. So it's a sum over all pixels from m equals 1 to large M of fx1 times fx1, or fxm. So this is the sum over m pixels. And I simply have this squared because this value and this value get multiplied, so they are squared plus fx2, 3, 4, 5, and so on. And for this one, which is this multiplied with this guy, I get this one over here, and then the others if I multiply x and y. But I always have the structure that I have the sum over all m elements corresponding to all my m pixels over here, and then the gradient in x squared, the gradient in y squared, and the gradient x times the gradient in y. Okay? So if I go through the individual things, what I have in here, this sum is always the sum over all m pixels involved. So all of those sums involve m pixels from small m equals 1, so from m equals 1 to m. So always sum over m elements. This is again the same notation as before. The first derivative of my image function in the y direction for the pixel m. Again here, this is the squared first derivative of my image function in the x direction evaluated at the pixel m, so at pixel m. And again, here, the sum of the squared first derivatives in the y direction. So simply take my first derivative. So for every of those 12 pixels over here in this example, I compute what is the first derivative with respect to x. Okay, I square it, put it here. I go for the second pixel. What the first derivative with respect to x? Square it, add it up. And I continue the whole process. And once I have that, I computed this element over here. Then I do the same thing for y. The first derivative with respect to y of this pixel, sum it up here. Second, third, fourth, and so on. And then I do this for x times y. And this way, I obtain those elements. So for computing those elements, the only thing I need to know the first derivatives of my image function, which I, again, can compute, for example, using the Wrobl operator. So just by applying the Wrobl operator, I can actually compute all those elements. Okay, so we said it's just a copy-paste from the previous slide. This is our matrix N that we have. Our X corresponds to the change in our offset parameters, and this is simply the Jacobian and the delta L, so the change in G minus F at the corresponding locations. Okay, the uncertainty in the shift. The uncertainty I have about the estimate of my shift after I converged is a constant multiplied by the inverse of our matrix N. Right? Something you should have seen in the past. So the uncertainty that I have about my estimate in X, so this estimate of my shift, is in this case, the variance of the noise the variance that I have in my signal times n to the power of minus 1, so the inverse of n. So the inverse of n is A transpose A inverted. So given that I know what A transpose A looked like, this was my A transpose A. As a result of that, the uncertainty about my shift depends on the inverse of this function. So this function, so what this equation shows me, it shows a direct relation between how accurately I can actually determine the shift and the gradients that I have. And there's a power of minus 1. So what it intuitively means, the larger my gradients are, the smaller the covariance matrix gets. So the more gradients I have in my image, the better I can actually align them, which makes intuitively perfect sense. So if you, again, have this example of a uniformly colored area, you want to match it with a uniformly colored area. There are no gradients, so I have no idea where this actually matches to. If I have a uniformly colored area, this matrix will have all 0 values because there are no gradients, so that means I have an infinite uncertainty. If I have, however, very steep gradients, so very perfect change, for example, from black to white pixels, I can actually align them extremely well. So if I have very large gradients, it leads to small values in the covariance matrix. Okay? So the important thing here to notice, there's a direct relation between the gradients that I have in my image, or the squared gradients, and how accurately I can do the matching, how accurately I can determine the shift. Okay, now let's have a look into the covariance matrix of the gradients. So we can, of course, also say for my gradients, I can compute my covariance matrix. And if I now assume that I have a zero mean in the gradient in x and y over my image, which if you consider the Wrobl operator, for example, which if I sum up all the values gave me a 0, that means typically end up having a zero mean function for the gradient over the image. So assuming that we have that zero mean, those elements over here, by just using the standard equation for computing the variance, I obtain these values over here. So again, it's this squared gradient, of course, this is a zero mean, simply with 1 divided by m. Same for y and for the off-diagonal elements of the covariance matrix with respect to x and y. And if we now look to these equations, we can actually see that those elements were exactly those elements I've seen before in the covariance matrix of the shift. So if I go back a slide, these were exactly those elements over here. So I actually find them here if I compute the covariance matrix of the gradients. The only difference that I have this factor of 1 divided by m, which is involved in here. So we can now simply copy both covariance matrices, the one we had before and the one I have down here. We can actually see and simply move this 1 divided by m out of my matrix. They can actually see that those elements are exactly the same. Again, what I see here is that there's a direct relation between the covariance matrix of the shifts and the covariance matrix of the gradients. They have a different factor here. And the key thing is this one is inverted, the other one is not. So there's no to the power of -1 here, but a power of -1 here. I can put that together. I can actually get the equation that the covariance matrix of the shift is a factor which depends on the noise in my image function and the number of pixels that I'm considering and the covariance matrix of my gradients. So this is an important information that we'll actually exploit very soon in this relation, that the precision of the estimated translation depends on 3 properties. The number of pixels that I use in my template. So the larger this template gets, the better I should be able to estimate my translation. Also, the smaller the noises that I have in my function, the better I can estimate my shift, also something which should be kind of intuitively clear. But the thing which may not have been clear from the beginning on is what I try to explain, that the gradients matter. So the covariance matrix of the gradients, or especially the squared gradients, given that it's a zero mean function, has a direct influence on how accurately I can actually localize one image inside the other. So the steeper the gradient, the better the matching. This is kind of the key take-home message. When you match those 2 images, you have to inspect the gradients of your image function in order to determine how accurately you can actually match them. So for a small example over here, let's say I have this, I want to check how well I can use this image to localize in this image, given I have the corresponding identical patch that I want to match it to, or a small patch of that. So it's just a transition from dark pixels to white pixels in 1 dimension. So these, I have all my pixels over here. These are my m pixels in this area. I'm going to simply write down the shift that I have, one estimate, sum up the gradients, which is exactly the same as I had before, just copying what I had in the previous slide. And if I now look to these individual values, so how do the gradients in the x direction look like? What are the sum of the gradients in the x direction here? X is this direction.
0.
So all 0. That means this value turns into 0, this value turns into 0, and this value turns into 0. So they are all 0. except this guy over here. This is the gradient in the y direction. It's 0 in this area as well, 0 in this area, but takes large values here at that edge. So there will be elements that these guys are non-zero. Okay. And this one is a constant, has the same number of pixels that I match, and assuming that we have this, the noise of the intensity values is a constant. So this is constant. The only thing which actually matters are the magnitudes of the gradient. So this turns into a matrix with 0, 0, 0, and a constant value over here. What this matrix means, we can actually interpret this matrix. We have an uncertainty value here, and we have no gradient over here. And since we need to invert this matrix in order to estimate the shift, that means we cannot estimate our shift in the x direction, but we can localize it in the y direction. So especially with a steep gradient like this, the result is based on this matrix that in the y direction, so in this direction, I can localize my image very well. So it's very well suited for matching. But in this dimension, I can basically, if I have the same image, I can slide it up and down and have no chance to determine which one is better or which one is not. So for an image like this, there's no way that we can estimate the shift in the x direction. We can only estimate it in the y direction. This is what this matrix tells us. So again, this should emphasize that the gradients matter. The magnitude of the gradients in the individual dimensions matter. So if we look kind of to 3 typical cases that we find, if this is our image, we can say, okay, we have gradients in the y direction and we have gradients in the x direction. So this is an area that we can typically localize very well. So this kind of should be indicated with I can estimate the shift very well. If I have this example, that's exactly the example that I had before. I can match very well in this direction, but I have a large uncertainty matching in this direction. And if I just a blob area with some noise in there, I can have no distinct areas of a very large eigenvalues of the covariance matrix of the shift. So I cannot localize this one very well. Okay. So what we've seen so far, we looked into least squares matching. How can we formulate the same problem that we used to, as in cross correlation, in order to find a matching, but now using the least squares formulation. And what we have done here, we analyzed how accurately we can actually determine our shift. And the key take-home message is, how accurately we can determine the shift depends on the magnitudes of the gradients that we have. The steeper the gradients in a certain direction, the better we can localize in this direction. In order to localize well in two dimensions, in x and y, we need to have gradients in the x directions and in the y directions. The steeper, the better. So if we perform our least squares matching, these are the precisions of the alignment that we can actually find. So what we have done so far is we looked into the least squares problem only taking into account translation. We haven't considered so far changes in brightness or in contrast. So the next step is now to generalize what we have done so that we can take into account more complex transformations. Because this was the goal why we started. If we would only deal with translations, we could use cross-correlation. But now the question is, what happens if we want to have more complex geometric and radiometric transformations? So consider we have 2 images which we want to align. The alignment at this point P in this image number 1 corresponds to this point, but they are even rotated, or in there could be, for example, a shear in there and a scale change. So we have an affine transformation from one image to the other image. And we assume we have a linear radiometric transformation. That means we have a change, we can have a change in brightness and in contrast. So in this, with respect to the radiometric transformation, we don't do any change with respect to cross-correlation, but we can now take more couplings transformations into account between both images. And what we find is actually this transformation, the parameters of this transformation, TG, so that one image is aligned and fits to the second image. So this is now not a shift anymore. Okay, so this is our goal. And the nice thing is we can very easily generalize this. We don't have to go through all the equations. We only have to change the transformation that we specify. So our transformation says the coordinates in one image, the coordinates in the other image depend on those 6 parameters. So this is our translation, that's what we had before. What we additionally added are those 4 values here, which I can use, for example, to express a rotation, a shear, a change in scale. Okay, so these are the additional parameters that we have. 6 parameters for this transformation. And what we additionally said, we want to have a radiometric transformation taking into account changes in brightness and contrast. So I have my radiometric transformation, which says it's simply a constant or coefficient times the original image function plus an offset. So this is a change in contrast, and this is a change in brightness. So what I now need to do, if I don't know anything about those parameters, I can start with the identity matrix. That means A1 and A5 take, for example, a value of 1, and A7 as well. So there's no change, just the identity mapping. And then I set all the other values to 0. This way I get the identity, and then I estimate all those parameters. So these are the parameters, the 8 parameters for my geometric transformation and my radiometric transformation. So the difference between what we've done before and what we are doing here now is before we just had 2 parameters, those 2 parameters. A3 was U and A6 was V. And the others were 0, 0, 1, 1, 1, 0. That's what we have done. The only thing which changes now, we go from 2 parameters to 8 parameters. But everything stays exactly the same. Of course, my Jacobians, my linearizations get more complex. So instead of deriving with respect to U and with respect to V, I need to derive with respect to all 8 parameters. So this again, the first derivative of this function with respect to x, with respect to y, and then of course I have to do this for all the other parameters as well. So I have exactly the same issue that I have my transformation. I need to estimate my parameters. I end up having exactly the same Gauss-Markov model, except that we have the more complex model that we have. So we end up in having a system of normal equations, which is not a 2 times 2 matrix, but an 8 times 8 matrix, because we have 8 parameters instead of 2 parameters. And my linearization gets a bit more complex. So you need to invest a bit more brain power in computing that. But the overall concept, the overall process is exactly the same. Again, I need to iterate. Nonlinear functions involved in here. Now, just an example, what we can actually do with this is, if we have images of a certain size, so in this case 32 by 32 pixels, I can actually estimate, based on this, how well I can align them with another image. You can actually see, based on the structure of the image and the gradients that we have, we get different uncertainty ellipses illustrated over here. So this is one which I can actually localize very accurately in X and Y shift is this here. So it's just one spot over here, so I can actually quite well align them. If I have a lot of grayish areas or indistinguishable areas, this actually gets, the uncertainty gets much larger. Or along this edge, I can localize very well in this direction. So the uncertainty is small in this direction, but it's large in this direction. What I can do is, based on this information, I can estimate how accurately I can actually align this image patches with the corresponding second one. And it turns out, especially for these accurate cases like this one, we can actually go down to a 20th pixel resolution. So get an alignment using the least squares formulation, of course having here a large number of observations, so 32 by 32 pixels, so 32 by 32 observations. A large number of observations in order to estimate, for example, 2 parameters or 8 parameters over here. And given that, I can align those image areas very, very accurately. So if we now compare the cross-correlation method to the least squares method. So least squares matching and cross-correlation are equivalent under the assumption that we have a radiometric that the geometric transformation is just a translation, because that's the only thing that cross-correlation can handle, and that the radiometric transformation only makes changes in brightness and contrast. And if I use my subpixel estimation, they kind of compute the solution for the same problem. The least squares matching, however, is more general, as it allows for arbitrary radiometric transformations and arbitrary geometric transformations. So if I have an additional knowledge or more complex transformations, I should go for the least squares matching. My model gets a little bit more complicated, but instead of a 2 by 2 matrix, I obtain, for example, the 8 by 8 normal matrix, but this is nothing which is large in the classical sense of problem that I need to solve. Compared to cross-correlation, where I really would need to iterate over all possible configurations in order to find the good match. However, the least squares matching needs an initial guess, and I need to have some ways for starting with an initial guess. If I'm far away from the initial guess, I'm not likely to find the right match. So really the initial guess matters. This, and kind of the cross-correlation techniques basically solve this issue of finding an initial guess by simply an exhaustive search, simply trying all possible configurations. This works only in low-dimensional spaces, not in high-dimensional spaces. It would be simply too many combinations that one actually would need to try. So kind of to sum up this chapter on matching. So what we have seen in the lecture today and in the lecture last week was that finding correspondences between images is an important task. That's hopefully clear. And one of the key tasks that we're addressing here, especially later on in Photogrammetry II, is we need that in order to do 3D reconstructions. So in order to estimate the 3D shape of an object or 3D location of points in the scene, we need to have correspondences between images. We will also use this to estimate from which location 2 camera images have been taken. So what's kind of the relative transformation between the location where camera number 1 took an image and the second camera took an image of the same scene. By knowing correspondences, we can actually compute that. And we looked into 2 different techniques for doing that. The first one was the cross-correlation technique, which was kind of easy to do, easy to implement, use exhaustive search, and we can actually even do a subpixel accurate alignment of the image patch with respect to the other image. And then we introduced today the least squares matching as a generalization of the cross-correlation technique, which allows us to deal with transformations, especially geometric transformations, which are not just pure translations, but which are more complex. So this is the more general approach, but we have the drawback of needing an initial guess in order to do that. Okay, that's it from my side for the matching chapter. What the next step will be, we actually use those findings to find good, or to set up good point features. So what we want to do is, given that we have this knowledge that we can match well if the gradients have a certain structure, we say, let's flip the coin around and try to find points in my image that are actually well suited for matching. So we don't want to match everything with everything, we just look for points in my images that are actually well suited to perform such a match. So for those points, we then can obtain an accurate 3D reconstruction. So the next step is to build on top on what we have done so far, especially the slides with the gradients. So this one over here. So what we'll exploit is this information. This will be key for the next topic. Is trying to find area as an image where this matrix has a shape which is well suited to support the matching process. So, for example, if I have a stereo setup with 2 cameras, I process my images and say, what are points in those images which are well suited for doing this matching, which I can localize very accurately. And then I say, okay, these are kind of good point, distinct points. And then I use these points in order to do the 3D reconstruction. This is kind of the next step, and this leads then to the so-called Förstner operator, which was actually developed by Wolfgang Förstner, as a technique for finding good point features to establishing correspondences, for example, in a stereo setup. But that's something which I'm not starting today, so we are finished a little bit earlier today in order to kind of reduce the workload a little bit more towards the 10 hours or 11.5 hours, not more. So I'm done with the course for today, and I hope you have a nice DS tomorrow, and we see each other next week, but on Thursday there will be exercises given by Susanne. Thank you very much.